Hello. So this is actually my 5th year at Securi-Tay'er in a row, so I'm quite happy to be back. It's awesome. Okay, so this is a bit of a weird talk in that it's sort of changed a bit. I'll explain why in a minute, but there's an asterisk next to implementation for reasons. So, hello. So, I'm Graham Sutherland. I used to work for Portcullis, and then we got bought by Cisco, so now I work for Cisco. I'm on Twitter, Stack Exchange, you can email me, whatever, I don't really care. Mandatory slide. So, things went a bit wrong with this talk. I did the usual thing of, you submit a talk, and then it gets accepted, and then you do the work. That's how you do it, right? And then last week I got ill, so I didn't do the work. So instead, I've sort of flipped this talk around a little bit. So it's going to sort of focus more on the approach and the tool that I wrote. Yeah. So this talk is a little bit different to what might have been advertised, but hopefully it'll be still interesting. So, how many of you here have done a web app or infrastructure assessment and scanned SSL TLS configuration? Cool. Right. So, you do a pen test or whatever, and you check HTTPS or whatever that's running TLS or SSL. And you want to know what Cipher suites are enabled, what version of TLS or SSL versions are enabled, so that you can tell how secure it is. But do we really do enough in that regard? Are we really covering that domain of SSL, which is a fairly big protocol, and, well, I say fairly big protocol, in terms of the number of vulnerabilities that can exist because it's crypto, and crypto is hard, and because it's code, and it's hard to write secure network code that's parsing binary data and things like that. Anybody who's ever seen ASN1 parsing vulnerabilities and the number of them can sort of understand how many vulnerabilities exist in that space. And also, I'm going to look at sort of what tools do we have at the moment and whether we can do any better than what they do. So here's a bit of history, fairly abridged, of SSL issues-ish, so stuff around SSL or SSL implementations. So let's start out with BEAST in 2011, so that's a sort of protocol issue. Then you've got crime, which is around compression issues. Then you've got breach, which is a sort of evolution of that. So these are sort of side channel attacks. And then you've got Heartbleed, which I'm sure all of you saw all the wonderful marketing around that. Then you got Poodle, and then the magic version of Poodle that worked on TLS as well. That was quite an interesting one, because it shouldn't have worked on TLS, but it turns out that some implementations implemented, just basically copy-pasted the SSL v3 code into their TLS implementation, even though it wasn't actually compliant with the TLS spec, and therefore we got Poodle vulnerability on TLS as well. Then we got Logjam, which was very interesting because there was all sorts of fun nation-state stuff around that. And then Freak, Suite 32, we're seeing quite a few SSL vulnerabilities. And I was having a chat with somebody who might have been like Jack earlier when we were in the bar, and was saying, well, it seems like there's been a lot of these SSL vulnerabilities and these TLS vulnerabilities that just sort of popped up out of the middle of nowhere in the last sort of 5, 6, 7 years. And everybody just sort of assumed that the OpenSSL guys were a big team and it was all open source and all that, and then it turns out it's like 5 dudes on a 40 grand budget. Yeah, not everything is great. So, this is sort of a summary of the problems that I see with the current state of SSL TLS server code, and also client code to an extent. So the many eyes principle only works when many trained eyes are actually looking. So OpenSSL, everyone went, no, it's fine. Google are funding them, I think, maybe. And it turns out that nobody was really funding them, and nobody was really looking. So the whole, open source is great because everybody can look at the code. It's like, you can, but is everybody? And is everybody who's actually trained in security and actually looking for security vulnerabilities? And the answer is, a lot of the time, no. So the more time people put into this, the better, but it's a slow process. Custom implementations will always exist due to niche requirements. So there's a bit of a sort of, I suppose case study is the businessy term, and now I work for Cisco, I have to use businessy terms. Yeah, so there's a bit of a case study of, who's familiar with F5, big IP? Okay, so they make really big routers and some security products, but mostly really, really big routers, like core internet stuff. So they have to write code that does weird things with SSL, like working out certain, routing absolute tons of traffic based on server name indicator SNI from SSL. So they have to have some weird code that isn't standard. It's not like just OpenSSL or LibreSSL or whatever. They have their own thing. And the same goes for like endpoint load balancing, all of that kind of thing. So there are weird implementations that are not the standards. And you will often find really odd behavior in those that you would normally expect never to exist inside a normal SSL stack. And then, of course, we all know that writing secure code is quite hard. Cryptography is quite complicated. And writing secure crypto code is bloody impossible. You could put a team of cryptographers and a team of developers who are trained in secure dev together and tell them to write a TLS implementation, and you would still find bugs. Because the problem space is so huge. Even if you're just like, if you start out thinking, oh, well, what about, we're just going to think about memory corruption bugs and logic flaw. Okay, what about constant time? What about side channel attacks? What about differential power analysis? So, and then, what if you compile this code for a different architecture? Now that's got to be constant time on that as well. So if your compiler starts emitting some assembly that isn't constant time anymore because an optimization exists for that particular architecture, suddenly your secure code is not secure against that particular side channel attack. So building secure code is really, really hard when it comes to crypto. And then, of course, you've got inbuilt protocol deficiencies in TLS. This is why we have lots of TLS versions. TLS v1.3, I was hoping that we would finally fix a very, very long-running problem with how TLS does authenticity and encryption with like CBC mode and things like that. And we didn't, because it was too hard. It wasn't. But they said it was too hard. So basically, the problem is that we've got these like layers upon layers of changes and additional RFCs, and the protocol becomes so convoluted when you've got backwards compatibility, which means the code has to have all of these weird edge cases in its state machine, which makes things even more complicated. And of course, more code is more bugs. But then, does that just apply to a single project? Every time you fork SSL and make a new SSL project, so of course we've got the TLS implementation in Windows, then you've got OpenSSL, LibreSSL, PolarSSL, LibNSS, there's like BearSSL and a bunch of others. Whatever the hell Big IP use for their F5 stuff. Citrix, I think, have their own thing as well. The more projects you have, that's still more code. So if I'm just looking for arbitrary SSL bug, now I've got even more code to look at. So it's quite difficult to solve as a problem. But it also means that instead of just looking for, like, I don't know, what SSL ciphers are enabled on a box, why not look to see if you can exploit any of these problems at the same time? And that'd be quite nice. So the current state of affairs sort of summed it up a little bit, but in terms of pen testing it, we have a small number of tools, fairly small, that most people use. There are some crude approaches. I will discuss at least one of those crude approaches in a minute. It works, by the way. It's actually one of the most used TLS configuration scanning utilities out there, and the approach is amazingly crude. And I can say that because I know the guy who wrote it. And some of them are internet only. So some of them you can only do the scan from the internet with some service. So the first tool, SSL scan. Who's come across SSL scan? Hands up. Come on, must be more than Okay, fair enough. So SSL scan, it's one of the older ones in terms of at least what I've used. It's a pretty cool tool. You run it across a host. It tells you all of the ciphers that are enabled, what TLS SSL versions are enabled, blah, 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 blah. There's a bit of a problem with it. It uses OpenSSL. And when OpenSSL patched out SSL v2 support, that can no longer scan for SSL v2. So depending on whether you've got an old SSL library or a new SSL library, depends on, and it will do this silently, by the way. It will just completely fail to detect SSL v2 if it's there, if you've got the newer version of the library. So you update everything, you think, oh, it's all updated, it's great, it'll find everything, and then it finds less. So that's a problem. So the problem there is not necessarily the tool, it's just that it was a design decision that was made, which was affected by a third-party library, which then, in the end, resulted in it not being ideal. So you have to get like an old version of OpenSSL and compile it and drop the lib into place and make sure it's using it and verify. That's a bit of a pain. So, reliance on a third-party library, in this case, bit of a bummer. SSL Cipher Suite enum.pl by Pentest Monkey. Who has come across this? A few of you. Good. Excellent. I work with him, so I can slag this off. No, it's great. It's actually my favourite tool because, well, apart from mine, of course, but it's one of my favourite tools because it just works. You know why it just works? Because the way that it scans for SSL is, what he did is he went in Wireshark, made some SSL connections, and then worked out where the different fields were that he wanted to take to change, and then just dumped the entire thing as a bit of binary, and then just sends it as a packet. So it doesn't understand SSL. It just sends bytes, and then checks what bytes come back. Also, it's written in Perl, and I hate Perl. He loves Perl. So yeah, there's a limitation in that, because of course the approach there means that it can't understand contextual bugs. It can't do interesting things like, what if I want to mess with the record structure before it's been encrypted, and then send that encrypted packet? It can't do that, because it doesn't understand how to do that. So, for what it was written to do, it does a bloody great job, because you can just see all of the SSL ciphers that were enabled, and the other good thing is it flags them up for particular issues. So it will give you like a group summary of these ones are vulnerable to BEAST, and these ones are vulnerable to RC4 being crap, and various other things. And I've contributed a bit to it, but I hate Perl, so your next option, sort of like going after a fly with a bazooka. So I want to scan for SSL. What I'm going to do is I'm going to get an SS license, and then I'm going to get it to license, because that always works, in a VM. And now I've got an appliance on my box running in a VM to scan SSL, especially if it's Qualys as well. Just don't get me started on that. Yeah, that's a bit of a weird one. So if you're already doing network scanning, sure, and NSS and Qualys are great. But at the end of the day, if you can never be quite sure. I always like to have that, okay, I ran the SSL tool against the SSL, and I looked at the results and I verified them for myself. So while if you're just doing a generic network scan, yeah, they're great, and they can find all sorts of issues that it would take you months to dig out by yourself, and you would probably forget a bunch of them, and yeah. It's just not a very specific tool, it's quite bloated for the specific purpose. I can't disparage them, because I'm not allowed. This thing is freaking awesome for checking your server, your own server, not a client server, because it's on the internet and their domain will pop up in the list, which is public. Or you can tick the box to hide it, but I'm sure they get rid of all of those records. You know, there's definitely a retention policy that exists, which is we keep it all. Yeah, so SSL Labs is awesome. If you've never run it across your own site, if you host your own site, if you've never run it across it, because you're going to find all sorts of interesting fun. It is basically the most in-depth SSL testing tool that exists at the moment. But, of course, you've got the problem that you can only target things that are on the internet, so if you're sat in a data center directly plugged into something, it ain't worth squat. And of course, it's a little bit sketchy to run it on client stuff because then you're exposing, well, the combination of the IP address that you were just from, which is probably registered to the organization, which is probably not too difficult to work out that you're a pentest org, directed to the client's domain, and then you can sort of tie those two together and go, oh, look, we know who pentests them. So, a bit sketchy, but still a cool tool. I wish I could put a screenshot in there because it is cool. So the summary is some tools have technical gotchas, so like SSL scan, it can just silently not do things that you were expecting it to do. Some tools are hard to expand, so of course SSL Cipher Suite enum, it's written in a way that makes it quite specific to its original goal. It's very difficult to expand and detect other things. Some tools are bloated, in terms of this at least. Some tools are completely unsuitable. Like the SSL Labs one, you can't really use it in a pen test. And some tools are hard to maintain, going back to Perl, because nobody can read Perl. So can we do things better? And I love that the previous speaker used this exact comic, because it just proves the rule that there is an XKCD for everything, and it's usually this one. So, of course, I'm saying, all right, we've got all of these SSL tools, let's write another one so that we've got competing tools. But I think that's a good thing for tools. Because as long as those tools are being used to test for security stuff, the more tools you've got, the more likely it is that you'll find something interesting. It's cool to expand your horizons. So the goals of this tool that I wrote, sort of, is, yeah, scan for everything that SSL Labs does, was my sort of initial idea. I was like, can I get SSL Labs, not pay for Qualys, because that thing is a monster. Can I get everything that SSL Labs does and put it in a command line tool that you just fire, and then it gives you a bunch of data out the end? I would also like that to be cross-platform, because I'm a dirty heathen and I use Windows as my testing platform. But we've got people who use OS X, we've got people who use all sorts of flavors of Linux. We even had a guy who ran Gentoo for a while. He gave up. Oh dear. And if you knew him, that would be even funnier, because he's a Debian maintainer. Yeah. So I would also like it not to silently fail if the system's not set up properly. So of course we're back on that SSL scan issue. I don't want to have to rely on compiling things because I hate compiling things. And of course, as soon as you have to compile something, it suddenly becomes surprisingly not cross-platform. It's like, oh yeah, just compile this, it'll work. Yeah, okay. After the 6 hours of working out why GCC is outputting this particular failure. You see my inner Windows monkey coming out now. No reliance on magic packets, because again, that's just I would like the approach to be much more built into a real SSL implementation so that it can really understand the contextual issues that are available to sort of pull data from. Needs to be easy to maintain and expand, so it sort of needs to adhere to some reasonable development practices, which I know we're all so fantastic at as security people. Yeah, output documents not in a fixed format, because everybody has their own import modules for whatever report they're doing, whether they're pasting it into a Word document like it's the Stone Age, or whether they've got their own magic report software that they've got XML or JSON or whatever imports from. So I wanted to make it so that there's some sort of output module that you can take a report object and then transform it into a HTML page or just some XML or whatever, and then import it, or just use it as a report or whatever you like, or just have text. And then, of course, easy for a non-dev to contribute. So one of the big problems is that there's so many damn SSL bugs that come out. And I kind of go, oh, right, well, I really want to build a check for that. But there's an existing tool, so I'd love to just stick it in that tool so everybody can use it. And then you spend 2 hours trying to work out how the hell the tool works. So in this case, I wanted it to be, let's say, this particular Cipher suite, or these sets of Cipher suites, now constitute a particular vulnerability because we discovered something about whatever AES or RC4 was bad. like for example the RC4 case, we went, oh god, RC4 is actually quite crap, we would like to report that you're using RC4. Can we make it easy for a non-dev just to go, oh, all I have to do is say RC4 is bad, and basically copy paste a line in, and it goes, oh, yeah, okay, now I can detect that. So that would be quite nice. So the solution to my problems was Python, but more specifically TLS Lite. So TLS Lite is a pure Python implementation of TLS. It also does SSL v3. It's damn easy to understand because A, it's Python, and B, it was written by somebody who's actually fairly competent. It's got minimal dependencies. There's like a couple of critical dependencies that it won't run without, but it will very much complain if it doesn't have it. But I think they're like Python pip install, whatever the name of it was, so it's dead easy to get in. There's a couple of more complicated dependencies, but the more complicated dependencies are literally just things like you can install a library which makes the RSA math faster. Without it, it still works. So it's like a nice to have. So that's quite nice. It works on Linux OS X and Windows, so that's dead easy as well. Because it's pure Python, it doesn't have to pull in from any specific libraries. It's written by a guy called Trevor Perrin, and there's some additional contributions from others. There's the URL for where it is. And then a while back, Trevor created TLS Lite NG, which is a newer fork. The older one was on a different license, and then they ported it across onto a new license. And it's basically the now maintained version of it. And that's the one I've sort of forked from. And just an example of how easy it is to create a TLS connection with this. There you go. So you import socket and TLS Lite, because of course SSL sits on top of, or TLS sits on top of any TCP or even UDP socket, but let's say TCP. You connect to Amazon on 443 and then just literally wrap TLS connection on that socket, and it just works. And then, of course, because it's Python and it's open source, you can mess with those with that TLS Lite library, so that instead of doing the thing that the TLS protocol expects you to do, you can do something else, or you can tap into data at particular points. But yeah, just between where that triple dot is, you literally just write to the con object and start sending data that way. Okay, so the initial features that I wanted to start with was obviously Cipher suite detection, because that's what all the tools do, and this was where it was all sort of based off. But also include the TLS v1.3 draft spec, because that had come out literally as I started writing this. And also detect unknown suites, because it turns out that there's a lot of server implementations will just accept, at least initially, because you don't know how to talk to it, but it will accept Cipher suites that aren't specified by the TLS spec, like they don't exist. So that's weird. So they're like proprietary Cipher suites. And as far as I'm aware, there aren't really any tools that look for that at the moment, apart from like the big network scanners. And also look for supported curves when elliptic curve suites are enabled. That's kind of a quick win, because it's dead easy to detect them. It's literally the same sort of functionality as just doing normal Cipher suite detection. You just advertise a particular curve and just loop round, try each one, and then you know which ones are supported and aren't supported. Also looking for TLS extensions and feature detection. So ALPN and NPN, they're not strictly security features, but they're interesting from a privacy aspect. And the SCSV downgrade attack prevention stuff is quite interesting to look for as well. And then implementation checks. So looking for ServerRandom Entropy and MAC record validation. And these bottom two were both born out of interesting things that we found on tests or in interactions with clients. And I should say, both things that we found with interactions with clients when we were portcallers. They're probably not our clients anymore. So Cipher suite detection is fairly easy. So for each of the protocols in that list, try each Cipher suite number from 0000 to FFFF. They're just 16-bit identifiers. And basically, you send a client hello and say, I support this one cipher. That's all I support. And then if it says, okay, then you know it supports it. If it goes, oh, I don't know what that is, and sends you a fatal alert, then you know it doesn't support it. And then, of course, you've got your list of known ones that are real, and you can map those back, and if they're not in that list, you know they support something funky. So you store the accepted combinations, and then for each accepted one, where you know that the cipher suite is elliptic curve, like ECDH, ECDHE, that kind of thing, you then just, for each curve ID, go round and round again, and try connecting and just report that as being the only one that's supported. And then you store. So that's fairly easy. So next protocol negotiation was a specification that was adopted quite quickly, but it was never really properly accepted by the IETF, and they deprecated it really quickly. But the idea is that, so with the birth of HTTP 2, if you wanted to make a TLS connection, because the general rule is that all of HTTP 2 is over TLS anyway, you go to make a connection, so you do the client hello, you get the server hello back, you do your handshake, and then you start talking, and then you go, oh, by the way, I'd like to speak HTTP 2, and then it goes, oh, great, now you've got to drop that connection, create a new connection over HTTP 2, and then you've got to do another round trip. So this is in order to stop this round trip, this second round trip, and speed up the latency of connections, instead what happens is you can indicate inside the TLS handshake that you would like to speak a particular protocol. And that's an arbitrary string. You could put Bob in that if you really wanted. But in general, you'd say something like HTTP 2. And then it will go, oh, actually, I know that you're going to try and talk HTTP 2 to me. So the application layer can then go, oh, I'm going to go and speak that as soon as you come through, and you don't need to drop the connection and create another one. So detection for that's dead easy. You connect to the server using any TLS protocol. You advertise the NPN functionality as part of the TLS extension, and then you check if the server hello has an NPN response in it. If it doesn't, then you know it doesn't support it. So then they replaced it with this, ALPN. Oh, sorry, I missed one thing. There's a privacy concern. Because you're saying, I would like to speak HTTP 2, you can tell from that, because that extension is sent in the client hello, it's in the clear. So so if somebody's looking at that, they can go, oh, well, I know that that connection was a HTTP 2 connection, rather than I just know it's TLS. And anything can be under TLS, because you can put arbitrary binary through that. It's not generally a massive concern for most people, but it is a concern for Tor. There are issues with doing that through Tor. So ALPN is the newer spec, which is actually implemented now, and they got rid of NPN. But you will still find servers that support NPN. So again, it's the same thing. Same deal, really. You've got the same privacy concerns. Did I actually even edit that? No, I did not. It's basically the same. The difference, the difference was that NPN was weird because it required an additional message type in TLS, which is something that they like people not to do in their specs, which is, I think, probably one of the reasons they got rid of it. And ALPN works just as a TLS extension and a response. So they went, maybe not, switched over to ALPN. It's exactly the same. You basically, the detection is slightly different because ALPN protocols, when a particular ALPN protocol is accepted, it will only put the ALPN extension back in the server hello if you match up the correct ALPN protocol that it's expecting to see. So the TLS implementation might actually support ALPN, but you can't tell that unless you work out which ALPN, like the next protocols like HTTP 2 or whatever, that it actually supports. So if you don't hit the right one, you'll miss the detection, so it's a little bit harder to detect. But the great thing about this is that there's a bunch of draft identifiers, which are like HA hyphen and then 2 numbers, and there's about 40 of them. So you can just scan through all of those, and most TLS implementations actually include those as like just defaults, so you can spot them fairly quickly, which is nice. So an actual security thing to detect, rather than just a privacy one. TLS fallback signaling Cipher suite value, SCSV. So there's I'm sure some of you are familiar with sort of TLS downgrade attacks, but I'll go through a basic way of how they work. So Alice attempts to connect to Bob's server with TLS v 1.2. So Alice is like, yes, I've got an up-to-date client, and I can talk TLS 1.2. But Eve, man in the middle's that com, and goes, actually, I'm just going to send back actually, we don't support, Bob's server doesn't support that. So Alice's browser goes, oh, TLS 1.2 wasn't supported. Okay, I'll just try TLS 1.1, because that's the standard like downgrade and reconnect approach that most browsers do, because obviously otherwise you would only be able to connect over TLS 1.2. And anything else would just completely fail. So it tries again with TLS 1.1, and it says Eve can just man in the middle of that again, and just keep going and keep going and keep going until she gets to the very bottom of the protocol versions that are supported by the downgrade approach from the browser. So eventually you can end up on something like SSL v3 or SSL v2, horrendous. And Bob's server accepts the SSL v3 connection, and then Eve exploits it using some other bug, which is not good. So to stop this, we got this SCSV thing. So what happens with an SCSV extension is the initial connection is the same. So Alice tries to talk to Bob's server, tries with TLS 1.2. Eve, man in the middle of the connection, and sends back the TLS not supported. Alice's browser then goes, oh, okay, I don't think you support TLS 1.2, so I'm now going to send you a TLS 1.1 request. However, I'm also going to advertise an additional Cipher suite, which isn't really a Cipher suite. I'm going to say I support TLS fallback SCSV, which is what's called a pseudo Cipher suite, which advertises that the connection is due to a downgrade. Now, as part of that, the advertised maximum version in that SCSV fallback. Hang on. No, it doesn't matter. Sorry. So it sends this SCSV Cipher suite as part of it. And then Bob's server goes, oh, cool. You're trying to downgrade to TLS v 1.1. But then Bob's server goes, hang on a minute, I support TLS v 1.2. Why are you trying to downgrade to me for 1.1? So it goes, oh, well, this must be an attack. So it drops the connection and says, we're off. So it closes it with a fatal alert. So that way, you can't just man in the middle it and pretend like the connection didn't work. It will actually know that the downgrade attack was attempted and kick you back off. And for those of you wondering why you can't just tamper with the second packet that's coming through and remove the TLS SCSV fallback suite, all packets in the handshake are hashed together on both sides, and then the values are compared after the key exchange. So even if you tampered with that, as soon as the handshake finishes, it would detect a mismatch between what was seen on each side and then fall over, which is a really cool implementation. It's one of my favorite things about TLS. Very well designed from that perspective. Detecting it. Again, it's fairly simple. So you make a standard connection to the server, and then you record the max TLS version that was given, and then you connect again, supply a lower TLS version, and give it the SCSV Cipher suite. So you're basically emulating what both Alice and Eve are doing. And then if you get the fatal alert back, you go, okay, SCSV is definitely supported. If the connection is allowed, it either means that SCSV isn't recognized by the server, it's not supported, or it's implemented so horribly that it just simply doesn't work. Cool. So the next thing is ServerRandom. So ServerRandom is really important. So when you make a connection to a TLS server, you send client hello, and that client hello contains a client random. and then the server responds back with the server hello, and that contains a server random. And this means that both sides of the connection are supplying random data, which is then used with a pseudo-random function of PRF, combined with the pre-master secret, which is part of the key exchange to produce the master secret for that particular connection. Now, if you only used, I'll get this right, I forget which way around it is. If you only used one of them, client or server, I forget which one it is, it's probably both, you can just replay the handshake because there's no additional random data selected on one side, so you would just be able to replay handshakes over and over again and make connections as that client, which is not a good idea. So poor randomness of server random can reduce security significantly because if you can predict server random, then you've either got the potential to do replay attacks, or you've got the potential to maybe brute force whatever remaining randomness was exchanged, depending on the implementation. It's basically you're just reducing the entropy of the whole thing. And of course, repeating server random values can allow for replay attacks. So testing randomness properly is hard. If anybody has ever come across the die-hard randomness suite and tried to work out how the hell that works and what the hell the results out of it mean, you'll probably start to get into the realm of like probability theorem and all sorts of number theory, and things just get whatever that gif is of the guy with the explosions and his mind is blown. It's that kind of thing. So actually doing randomness, and also you need gigs of data. And if your server random values are only a few tens of bytes in each response, how many connections are you going to have to make to get enough data? That's going to take forever. So doing actual testing like that is really difficult. So instead you can do some heuristics. So the first one is repetition checking. So if you connect to the server a bunch of times, and if any of those give you the same random value twice, it's a pretty good indicator that something's very broken. And of course, if there's a repetition, then you've got the potential that you can do replay attacks on the handshake. Compression testing. Get a bunch of data, try to compress it. If it's highly entropic, then it won't compress much, or at all. If it's not very entropic, then it will compress quite easily. That's a dead simple way to check for whether something's actually like properly statistically random, and it requires nothing but like zlib. You can take the arithmetic mean, which is like the crudest possible measure, but it detects some sort of numeric skew. Serial correlation, which is essentially between each byte how many bits change, like which bits flip. And there's a statistical average of what you would expect with random data for that. And then monobit frequency, so basically how many times you see a 1, how many times you see a 0. So if that's roughly about right, then you know it's fairly good at random implementation. Some of those will pass if you just put like Java's math random through it. Some of those will not, which is good, because then you know that somebody's used a dodgy random number generator. So yeah, like the monobit frequency and the arithmetic mean will pass for a non-cryptographic random number generator. Those are just to detect for something really heinously bad, like it's just giving you zeros, or it's giving you the same value every time, or something like that. Whoop. Sorry, I'll go back one. Will I? Yes. Sorry. So the way that the tool tests for this is basically it does a bunch of connections. I think like 10,000 by default, but you can change it by a command line flag. Aggregates all of that data together into one big binary blob, and then runs all of those tests across it. So if it tries to compress all of that data, if you've got repetitions or anything like that, whereas detecting repetitions in whole responses is fairly easy, detecting repetitions like between responses can be more difficult. So for example, I don't know whether any of you remember the Debian SSL certificate generation bug, where instead of random data, they use stuff from the stack. That's not good. But it looked fairly random, so, you know, but it's just pointers. So the problem there, of course, is that if that sort of thing appears, it may look kind of random, but when you really actually compress it down, you go, oh, actually, that wasn't as random as I thought it was, and these sorts of checks, once you've got a big block of data, it work quite well. So yeah, side note, server random repetition is surprisingly common. This scared me when I found it. So I forget what it was. It was some random server, a load balancer or something. And one of our guys was doing a web app test, and he just happened to put, I can't remember what he ran across it. And he got some data out of the server random and went, that doesn't look very random, and kept running it and refreshing it and going, why am I getting the same values out of it? And it turns out that what it was doing is it had a global random value for the server random, which changed every second. So if you make more than one connection within a second, they all get the same server random. I mean, it's efficient. Yeah, it's a bit weird. So yeah, we found that one. There's actually a bunch. If you start digging around for CVEs, and also like Nessus entries and Qualys entries for server, just the keyword server random, you'll find all sorts of interesting bugs. So yeah, not as unexpected as you might think. So Mac bit validation, this is a fun one. So when I was saying earlier that I was hoping that in TLS 1.3 that we would have finally fixed one of the long-running sort of weaknesses in the protocol in terms of the way that crypto is done, Mac then encrypt. So Mac then encrypt means that when you take your plain text, you then compute your message authentication code, your MAC, your signature. You compute that over the plain text. You stick that MAC record on the end of the plain text, or before it, or wherever, and then that produces a record, and that entire record is then encrypted. Now, I would say something like 3 or 4 of the major SSL TLS bugs that were out were due to padding Oracle or other Oracle attacks against CBC Mac, sorry, not CBC Mac, MacLen CBC as implemented in TLS due to that, due to the fact that they use MacLen encrypt. And the problem is that because you have to decrypt the message to get to the message authentication code, any discrepancy in how that is decrypted leads to a side channel that you can use to determine something about the plain text. So, for example, BEAST was based on that. So, yeah, you can use that as a padding oracle. So it's a bad idea. Hence why I say, much trickery can be done. But this gets way worse if you don't check the MAC properly, because the padding oracles require all sorts of clever foo, and if you look at like the requirements for some of them, it's like, oh yeah, if you make 14 billion connections, you're like, yeah, okay. Like, maybe if you're Mirai botnet, you can make 14 million connections and do this attack. But it's also a DDoS, so yeah. But then, if you can find out that the MAC isn't properly validated, or just not validated at all, you can just arbitrarily start forging TLS packets, which is great. So there are actually known TLS implementation bugs where the MAC was not validated properly. So checking for this is a brute force approach. So in TLS v1.1, the verify data field was fixed at 12 bytes. So it's a 96-bit value. So your MAC for each packet was always 96 bits. If the MAC type in use was shorter than that, they would just pad it. In TLS v1.2 and later, they changed that. So it's each cipher suite that was defined previously has a 12 octet value. New cipher suites can now overwrite that. So for example, you could say like you've now got a cipher suite with SHA-256 as the per packet MAC. And then you could just have like a full 256-bit MAC per packet, or whatever. So for each of the number of bits in the MAC, so let's say 96 for default, you open a connection and you complete the TLS handshake. And then what you do is you compute a mask, so a bitwise mask value of 1 shifted left by whatever bit number you're currently on. So basically what we're saying is, start off with a bit on the far right-hand side of 96 bits in this bit string, and then the next time you're going to go to the next bit, and the next bit, the next bit, the next bit. Just 1 bit each time. And you're going to generate a single packet and send that over TLS, except the verified data part before the crypto, so that verified data field inside that TLS packet, you're going to flip that 1 bit. You're going to XOR that mask with it. So of course what you've done is you've caused that 1 bit to no longer be correct. So the rest of the bits of that verified data are correct, that 1 bit is incorrect. And if the immediate response back is not a fatal alert, then you know that the MAC checking on the server side is broken, because you know that you forged that 1 bit and it still said, oh yeah, that's fine. So it's not very common that you'll find that to happen, because most TLS implementations don't have problems with this. But historically, there are actually quite a few bugs around this. For example, there was one case when only the first byte was actually checked. So you could only have 256 possible values for the entire MAC. Which, of course, if you know what the MAC is expected to be, is your because it's on the plain text. So if you've got a known plain text, you can then compute another MAC such that the same first byte is the same, and then just replace the data. So that was fun. So yeah, so that's fairly simple to check in terms of you've only got to do 96 connections in order to check that all of these are actually validated. And of course, this gets a little bit more complicated in TLS 1.2 because then you've got to check based on the particular cipher as to how long that is. So a good trick with that is pick any arbitrary TLS v 1.1 or before cipher suite, check with that. Then pick your shortest and your longest TLS v 1.2 cipher suites that specify an overridden length, and that way you're going to cover most of your bugs. So yes, there really are bugs like that, and this tool was actually inspired by one of them. I might discuss it in a minute if I've got time. I know I'm running fairly close to the end. So the result is a tool called SSL X-Ray. It had another name before. It was called STCA. Nobody could remember it. So it's now SSL X-Ray. So it's a more modern SSL TLS scanner. It's written in Python. We've got a modified version of TLS Lite library. So it's been an internal alpha/beta, and I say that, basically what that means is I wrote it, it went into our internal repo, and some people used it, some people didn't. And then every so often somebody goes, oh, what happened to that tool you wrote? So it's not yet been published into the world. As I mentioned at the start, I got ill last week. I was hoping to really polish it off and do some additional research with it and make this more interesting, but I'm working on it. So follow me on Twitter or something, and I'll tweet when it's ready, and I'm sure somebody, if you don't follow me on Twitter, somebody else might find it and then pass it on to you. So that'd be nice. The future. So what I would like to do is add proper SSL v2 support. TLS Lite doesn't natively support SSL v2 because it's old and it's awful, but because it uses a completely different packet format. This is back from like the Netscape Navigator days. It's old as hell. Probably older than me. Yeah, so I'm hacking that support in myself. Client certificate support. Yeah, need to add that. As far as I'm aware at the moment, there are no standalone TLS Cipher Suite checking tools that support client certificates, as far as I'm aware. So that would be nice. Extending the MAC validation stuff to padding bits as well, because padding validation, of course, is very important as well. X509 certificate passing, so basically whenever you speak to the server, look at the server certificate that's given back, pass that, look for bugs in that, like SSL Labs does, like quite a few other tools do. And of course also look for broken, bad, and known weak certificates. So like I mentioned the Debian certificate generation bug, there are a few others as well. For example, picking an RSA, it's the RSA modulus of like 3. If it's a really small modulus, it causes all sorts of problems. Is it modulus? I can never Superfluous chain. So when a server responds with a SSL certificate, it can actually respond with 2 separate validation chains. Some of them can include like old, outdated certs and stuff. It's just not a good idea. And of course, then you've got the problem that if you pop either of those CAs, you can now cross-issue, even if you're doing pinning. Export grade DH, so like logjam. Same for common ECGH group detection as well. Support for DSA certificates for the like 6 people who use those. And saving scan traffic to PCAPs, because at the moment nobody seems to be able to do this as a tool. And in some cases, clients will say, "Can you store PCAPs of everything you do?" And it would be quite nice to be able to do that and just straight out of the tool drop PCAP, and that way you don't have to filter it. And yeah, it's a pain. How long have I got left? 5 minutes. Okay. That's a lie. Okay. So the inspiration for this tool actually came from a really interesting case that we had with somebody who is no longer a client. Not because of this, just because we got bought by Cisco and Cisco trashed all our old clients and just went, no, we'll start again. Okay. Vulnerability scanners are not above dodgy politics. So, LSV, large scanner vendor, versus an F5 TLS bug. So, F5 had this TLS bug, which they've called Sol 16970, which is not a very good one. TLS client finish message validation vulnerability. So basically there was an issue with the finish message not having its MAC validated or something like that, which came up in a scan, and it didn't go well. So the large scanner vendor detects this obscure bug in a PCI DSS compliance scan. The organization that we were scanning fails its PCI DSS because of it. And the org isn't massively happy because, of course, they're like, well, hang on, doesn't that mean that everybody that uses F5 stuff fails their PCI? And we go, oh, maybe. Wouldn't surprise me. It also wouldn't surprise me if most people just went, it's probably a false positive. Let them pass. No. So the organisation asks their QSA to ignore it as a false positive, and the QSA says, not unless I've got any evidence that it is actually fixed. So less than 24 hours go by, and the organisation calls back and says, so this large scanner vendor, they've just now issued a clarification that this is a false positive on all F5 systems, and that it's an acceptable PCI exception. And I read the bulletin and I go, it's kind of light on details, and it's very specifically worded towards PCI and very conveniently timed. So I Google the name of the guy who wrote the bulletin, and he used to work for the organisation. And my bullshit meter goes to 11. So this tool sort of came off the back of that, going, hang on, I need to check whether this bug actually exists, because I kind of can't trust this scanner vendor, because clearly there's a conflict of interest, and the timing was amazingly coincidental, particularly because I was on the phone with the person as they were reading that exact forum. Yes, it's a bit weird. Anyway, so the actual end, I promise that this isn't a lie, and that there isn't more slides after this, and I'll let you go get beer or whatever. Any questions? Aha, a question. Have we got the mic man to run around? Sorry.
Hi there. You were talking about server randomness. Mm-hmm. Is any of that work that you've done with the tool based on the thing that came out at Black Hat last year? There were 2 guys. There's an American researcher and a guy from Germany, and they talked about a theoretical attack against TLS 1.2, and the German guy had actually written a tool to scan server responses. Mm-hmm. And it's very interesting to see how some randomness came back as all zeros. 1, 2, 3.
I hadn't seen that.
Go and have a look at the Black Hat 2016 talk. It was quite interesting, actually.
I will. Yeah, I'll have a look. Thank you for that. Anybody else? Oh, we've got some at the top. Going to make you run. It's cardio.
So you mentioned with the signaling Cipher sweep value that to ensure that there was no tampering of this downgraded flag,
Yep.
There would be hashing on both sides, right?
Yeah.
Why wouldn't that work for just ensuring that there was no downgrade attempted?
Right, because you're just dropping the packet. So on the first connection, you just completely drop the packet and kill the connection, so that the server never even sees that first request. So because you're dropping it in the first connection, the browser goes, oh, okay, that failed. I'm going to now try to connect again with a lower protocol version to see if that works. It's like a backwards compatibility issue. So because you just completely dropped that first connection, there's no room for tampering because it doesn't matter. You've just dropped it completely.
When you were saying about the downgrade protection, one of the solutions being to hash off the packets on both ends, and then after the key exchange, communicate them. How do you ensure that the two hashes are shared after the key exchange securely? Because surely, theoretically, if you can break the connection quickly enough, you can then intercept the communication of the two hash values to be correct.
Right. I've forgotten how that works. So when I said that it's a really well-engineered thing, just trust me. And then read the TLS spec, because it does say, I just can't remember off the top of my head exactly how it does it. I remember reading it and going, oh, that makes sense, that's really cool, and then immediately forgetting exactly how it works. So yeah, that's the one part of TLS that I can never remember how it works. Google it.
And was it a false positive in the end? I have to know.
Maybe. I actually can't remember. Google it. If that answer is on Google, then we are in trouble. I actually can't remember, to be honest. That might be a lie. It might not be a lie. Anybody else? Cool. Thank you.